Okay, so last time we started holomorphic foliations by curves. So let me recall you that we are working now with complex manifold X, so compact, complex manifold. And we have a holomorphic foliation by curves on X. So L is a holomorphic foliation by curves. We do not consider foliations of a higher degree. So by complex curves, I mean therefore by Riemann surfaces, yes? So let me roughly remind you that that means that X is a union, is a disjoint union of leaves. And each leaf is a Riemann surface, a complex curve. And they agree in the sense that you have flow boxes, okay? So every piece can be mapped to such thing, yeah? Where this is a disk and this is a polydisk of dimension n minus 1, and n is a dimension of x bigger or equals than 2. Okay, this is a foliation by curves. We also had a notion of a form which is directed by L, a form which is positive on L. So we considered a 1-1 form, omega, such that for any vector which is tangent to leaves, which is tangent to our foliation, well, that means that I have some point, I have some leaf passing through this point. So to the contrary with this notation, I'm always using the following notation. If I have point and a leaf through this point, I denote it by LZ, okay? And we have a vector which is tangent to the leaf at this point. So the condition is that our form is positive on the vector, on the B vector V bar. It should be strictly positive. Okay? So in other words, in more intuitively clear words, omega is the area form on the leaves. It measures you area of the leaves. Now let me recall you, well, what is my aim? I don't know if I will achieve my goals today, but my aim is to develop some kind of Poincar-Bendixson theory for the holomorphic foliation by curves on complex compact manifolds. And in order to do so, to prove something like Poincar-Bendixson theorem, I will need to break compact foliated pairs. Okay. So X together with L is called a foliated pair. So I want to break foliated pairs into 3 disjoint classes, and try to explain you what is going on in each of these classes. This is my goal. And now let me recall you, well, I'm continuing. Let me recall you that we have de Rham operator on forms D, and in complex analysis you can present it as D bar plus D without bar. Yes, you all know what is that. We can introduce another operator, DC, and well, it is I over 2 D bar minus D. Sometimes one puts some other coefficients, but always with I. And now DDC will be I DD bar. So this is a real operator. So it maps a real form to real form because its conjugate will be itself, equal to itself. Small exercise for you. If n is equal to 1, if you are in dimension 1, then DDC is 4 times Laplacian. Yeah, okay, on the complex plane. Okay. Recall that the Laplacian you can write as d over dz, d over dz bar. Okay, this is more or less the same. Well, and now I shall call, this is definition, we shall call omega pluriclosed if ddc of omega is equal to 0. Omega is a form like here. So we have 1-1 form. Well, okay, you can say this about any form. But in our setting, we have 1-1 form, which is positive along the leaves. And we ask this form to be DDC closed. Manifolds, foliated pairs, foliated pairs admitting pluriclosed taming form. Taming means this. This is a taming form. So foliated pairs admitting pluriclosed taming form, we shall denote as T. Class all foliated pairs, which has, well, so what is that? For example, if your manifold is scalar or projective, yes, then you have Kähler form. Kähler form, first of all, it is positive, so it will be taming for any foliation. And second, it is closed. dc of this is equal to 0. So Kähler, any foliation on Kähler manifold is from this class. This is a big class. Now, okay. Now we can characterize, we can give a characterization of this class. So proposition let XL be a compact foliated pair. So a compact complex manifold with one-dimensional foliation bar curves without singular. Okay. Everything what I'm saying is valid also for singular foliations, but we consider only non-singular foliations. Then either there exists a DDC closed taming form like that, okay, or there exists a non-trivial positive DDC exact 1-1 current directed by L. Okay, so what is that? Current directed by L, we more or less know what is that. When we discussed foliated cycles, we already had currents directed by L. So what is that? Current is one current is a distribution of complex planes, which is not continuous, which is measurable only. So distribution of complex planes, and current directed by L, it means that these complex planes are tangent to the leaves. You have some distribution of complex planes at almost every point. It is not defined everywhere. At almost so its distribution is measurable. So it's not continuous, but it's not very bad. And at almost every point, it is tangent to the leaf, and the action of this current so you have this vector field. So locally it looks like locally at every point this is something like V bar I over 2 at point Z, more or less, with some coefficient, okay? So this is a vector field. So you can apply your form on this vector field. You get a number. So 1-1 form is a linear functional on 1-1 vectors, okay? So you can apply it, and you can integrate, and you integrate this over the x against some radon measure, Borel measure. Against some Borel measure. Okay, that's enough. So you have some fields tangent to the foliation. You can evaluate, you can take form, evaluate on this vector field. You obtain a measurable function, and you can integrate it. So this is a form directed by L. I'm sorry, this is a current directed by L. So what does it mean that it is DDC exact? So this current is of B dimension 1-1. So there exists, that means there exists a current, I called it S somewhere, of B dimension 2 such that DDC of this S is our T. So it is very strong condition in particular, this t is closed. dt is 0, okay, because d times d is 0. And so in particular, this defines you a what? A transverse measure, in particular, okay? But it's more than that. Yeah, so ddc of current of b dimension to 2 acts on forms, on 1 forms as, by definition, as S on ddc of omega. ddc of omega will be 2 form. So this will be b dimension to 2 current. Okay. And now my first decomposition of all foliated pairs. So these are all foliated pairs. So all foliations by curves on compact complex manifolds. So according to this proposition, which is proved in my lecture notes, and it's not really difficult. It's I even had a plan to prove it here, but it will not work. Okay, now we have tamed foliated pairs. The nice pairs which have such taming form as here. So, plus disjoint union, exact foliations, which I show foliation which admit exact current, I will call them exact. And now let us see some examples. What does it all mean? But by the way, okay, so now let me say one thing about the proof. It should not be completely mysterious. So, for example, let us understand that existence of such current is an abstraction for existence of taming form. Okay? So what we have that if t is such, then omega, then t evaluated on omega should be positive. So why? Because t is a positive current and omega is a everywhere positive form tangent to L. So this number should be positive from one side. But this is equal to ddc of this S, which exists on omega. And as I told, this is S applied on ddc on omega. And if this is 0, if it is pluriclosed, then this is 0. Contradiction. So this guy is an abstraction for, and vice versa, using Hahn-Banach's theorem. After all, you can prove the inverse statement. Okay, fine. That was enough about this. And let me give examples. So better I show you some examples. First example I shall design here because I will use it in several occasions. So you take, this is a Hopf surface, complex manifold of dimension 2, which is C2 minus 0 factorized by the equivalence relation Z equivalent to 2Z. So how you can see this manifold? You take in C2, you take the unit sphere S3. So sphere of radius 1, and you take sphere of radius 1/2 of radius 1/2. And now you well, here is 0. you identify z with 2z. So you have this shell between two spheres, and you glue the boundaries. You identify the boundaries. For example, on the real plane, not in C2 but in R2, you take unit circle, you take circle of radius 1/2, you consider this annulus, and you identify z with 2z. You got what? Torus. You got a torus. But this is something like a torus. Well, on this manifold, there is a positive form, which is positive everywhere, so it will be positive for every foliation. Not only along the leaf, but everywhere positive. And this form is omega I over 2 dz1 bar plus dz2 bar divided by the norm of z square. This is a everywhere. This form is positive in all directions. So whatever foliation you take on this surface, it will be positive along this foliation. No problem. Such positive form exists on any compact complex surface. Well, I shall not discuss this. On the Hopf surface, here is. And now DDC of this. DDC of this. Okay, you should differentiate 1 over z squared. So twicely by z2 and twicely by z1. So plus d over z2, d over z2 bar, and you should differentiate 1 over z squared. Okay? And we had what? I donc minus 1 over 2. Okay. Now, what is that? Who can tell me? This is a Laplacian in R4. And this guy is a Poisson kernel. Okay. So Laplacian of the Poisson kernel up to some constant, which I don't remember, is equal to what? To delta function at 0. But we are away from 0. Outside of 0, this is 0. So our form is truly closed. The last thing to see is that this form is invariant under our equivalence relation. But in fact, if you put instead of z 2z, everything can cancel. Okay, so this is form well defined, positive on the Hopf surface, and plus it is DDC closure. Okay. Now, as I told, well, okay, let me prove this probably. I want to say that such form exists on all complex surfaces. Oh, it immediately follows from here. Suppose, so an alternative is existence of this current. So otherwise, okay, to exist, such omega exists on any xl where complex dimension of x is 2. Otherwise, we would have this current S22, and was this current as b-dimension 2 on the manifold, on the complex manifold dimension 2. It is a current of highest dimension. It acts on forms of higher dimension. It is a function, a distribution. This is a distribution. And DDC of this distribution is form which is positive on the leaves. So, but in dimension 1, we know that DDC is a Laplacian. So this function is subharmonic, not harmonic, is a subharmonic along the leaves. Okay, this is thing, and this is not zero, not identically zeros. Okay, exist non-trivial. Okay, so S is subharmonic when restricted to the leaves of L. But then it should be constant by the maximum principle. We are on compact manifold. We have some function. Okay. And now we take somewhere maximum. At some subharmonic. Okay. Take leaf closure is compact. There is a maximum of subharmonic function. And this is a contradiction. You cannot have maximum. It should be zero. It should be constant. And so DDC should be zero. But DDC is not zero. Okay? So, but on dimension 3, so now this class of tamed foliations, includes all scalar foliations, all foliations on scalar manifolds, and as well all of dimension 2. But starting from dimension 3, there are foliations which are not in this class, and this can be seen already on the Hopf threefold. Now we take Hopf manifold of dimension 3. Well, this is C3 minus 0 quotient by the same equivalence relation. Well, picture is the same, only this will be a 5-dimensional sphere. Okay? So everything else is the same. On this, now, okay, foliation which I shall consider on both on Hopf surface and on the Hopf threefold will be the vertical foliation. So I take vertical lines. So this is a direction of coordinates z1, z2, and this is z3. So you fix some point, and you took a line through this point. How it works? So it intersects this shell like that, but then it is equivalent. 2z is equivalent to z. So it comes here. And then like that. These are equivalent, and then so this guy projects to union of two things, and it continues like that. So every leaf, and here is a C, is a C1, C2 is in some point on the Z1, Z2 plane. So every leaf, C1, C2 is C, is a complex line, is a B-holomorphic image of the vertical complex line. Every except 0. So, every leaf is C except this which passes through the origin. If C1, C2 is not 0. But the leaf which goes through 0, so it's a torus. You know, you have annulus. This is the annulus. And then you have to identify boundaries, like here. So the central leaf is a torus. Okay, this is a well-defined foliation. And now, consider the following form. Theta is minus I over 2 dz1, that's like that, dz1 bar, plus dz2 bar, over norm of z1 square plus z2 square. Okay, it's well defined on our surface for the same reason. And ddc of theta, so it's 1-1 form, therefore it's 2-2 current. And ddc of theta you can compute, it is a volume of 4-dimensional ball times current integration of the over the central leaf. So theta is our S22, and integration over the leaf is our T. So we have a ddc exact positive current, which is very simple. It is a current of integration over the compact leaf. And therefore, as we know, it is an abstraction for the existence of ddc closed taming forms. Okay. Well, and now, so that's finished. And now I want to state a Poincar-Bendixson theorem, because I'm afraid that I will not arrive to it. So I shall state the final result, which is not in your lecture, in my lecture notes. I was not planning to talk about that, but then I saw that. Well, I should explain why I'm doing that. So theorem. Well, before I state it, okay. Before I state it, so recall that in the Poincaré-Bendixson theorem, Poincaré-Bendixson theorem told us that the limit set of a trajectory which goes through the point x is an orbit or a polycycle. Yes? So it's a closed trajectory and gamma x approaches to it. Not just any, but or polycycle like that, some trajectories joining some singular points, equilibrium points, and again something which approaches this. Okay? And so on. And we remarked in the proof, it was clear that the holonomy map, so if you take transversalis, then Poincaré first return map, or holonomy map, let me recall you what is that. You take a point, you consider the trajectory, it goes, and then intersects it's this another one time more. And we remarked that this holonomy map is contracting. So the limits of leaves in Poincar Bendixson, the limiting leaves are contracting. They have contracting holonomy. Well, so it explains, and I defined last time what is the limit of the leaf of the complex curve. Okay, so if L was a leaf of a holomorphic foliation, so limit of this leaf, well, it is the same, is the set of all limits, all points in this leaf such that they go to infinity inside of this leaf, they leave every compact. Okay? So it's the same. And what leaves can be limits of such thing? Okay, so it's natural to consider leaves, complex curves, complex leaves, which have contracting holonomy. So what does that mean? We take, well, let this be our leaf in complex manifold. Well, let Z be this point through which this leaf passes. Take a curve, a closed curve, which is not homotopic to 0, as here. This circle is not homotopic to 0 inside of itself. Okay? And then you take a transversal. You can take a transversalis, D, well, which is biholomorphic in this case to the polydisk of dimension n-1. Okay? And you have a holonomy map. So we defined a global pseudo group of, in this case, biholomorphisms, and then along every curve you obtain a holomorphic map which is defined by the homotopy class of this curve of this transversalis D centered at Z to dz. Okay, it's a holomorphic. So our foliation defines for every such curve some map, which is a holonomy along this curve. Which is the same as in Poincar-Bendixson theorem. Let's say that this holonomy is contracting. This is contracting as here if all eigenvalues of its differential at this point are by modulus less than 1. So it contracts. And now we see that the limit leaves somehow, it's not exact statement, but somehow they should have curves with contracting holonomy. So we should look for curves, for leaves which have loops with contracting holonomy. And now theorem. Let L be a holomorphic foliation by curves on a compact complex manifold X such that the universal covers of leaves are biholomorphic to C. So such foliation is called parabolic. So let us consider a class of parabolic foliations. Let L0, let some leave L Z0 contains a loop with contracting holonomy. Then this leaf is a compact complex curve. That means, because we are not in singular case, E T0, this leaf is a torus. So we have a complete analog of Poincar-Bendixson theorem. Well, in Poincar-Bendixson, in the case where there were no equilibrium points, and we consider this case, we don't have singular point. Then we don't have polycycles, forget about that. And we have that the limit sets are trajectories. The same is here, limit set are toruses, which are leaves. But as I told, that everything which I said here works also for singular foliations. And then the situation is more complicated. There can be some special spheres, special Riemann spheres, much more possibilities can happen, but they are all observable. But let us concentrate on that. And now let's go back to our Hopf surface. So now again, I consider not Hopf threefold but Hopf surface. So V1, C2, this is Z1, Z2. We have this vertical foliation. Okay, fine. And we have this central leaf. Okay, let me. L0. Now you can take a curve here, which I describe with 2 points. Well, what that means that this curve is gamma is a set of 0, Z2, so Z1 is 0, and Z2 is by modulus equal to something in between, 3/4. So it's a circle here. And one can prove that this loop has contracting holonomy. And this leaf is indeed a torus. Okay. Now, so what can I say about the proof? The proof breaks into 3 cases, and I will discuss only one case. And this case is when the most terrible case, when our foliated pair is exact. So it does not have taming form. Now, if you have taming form, you can do something, you know. You have taming form, you can consider. And you have just some current, terrible current. But nevertheless, it works very in the spirit of Novikov's theorem, of the proof of Sullivan of Novikov's theorem. So the proof which I presented to you is not a proof of Novikov, it's a proof of Sullivan. So what we shall do, let me, how to make this quickly. Yeah. So let we have this point z0 and leave L z0 passing through this point. And let's take a transversalis D, well, which is in this case be holomorphic to a polydisk of dimension n-1. Okay. And we know and foliation looks more like that. Now we know that there is a DDC exact current. So we know there is a current. I really even don't need the DDC exact. I need it is closed. But then by the things we proved, there exists a transverse measure. Where transverse measure is defined? Transverse measure is defined on all transversalities. Yeah, so you define, you cover your manifold by flow boxes, which have transversalities. There you have measures which are invariant on the holonomy group. But then you take any transversalis and induce measure on that, okay? But so we have transversalis and we have measure on it. So forget about all transversalities, remember only this, and this mu be a measure on D. Okay, fine, you have a measure. And now this measure is invariant under the action of the holonomy group, or holonomy pseudo group. But holonomy pseudo group acts on our transversalis. We have this holonomy, we have some special curve here, special gamma, such that when you go around this curve, you induce a holonomy here which is contracting. So we have a holonomy map which corresponds to this curve, which maps dz0 to dz0, and measure is invariant under this action. So mu of h gamma of D is the same of mu of D. But this is contracting thing. Now look, what does that mean? You have D, you have h of D. H gamma of D. And the measure here and here is the same. What does that mean? That means that this measure is 0 here. And you continue so. And you got that your measure is 1 point. Therefore, your measure is a delta function, delta measure. Okay, with some constant. Okay? Now, that's first thing. And now imagine that this leaf would intersect the same transversalis. So this is a leaf, it goes somewhere, and then it returns, for example, here. But then we already considered this example with delta measures, and then this measure should be delta also here. But it's not the case. So this leaf intersects every transversalis only once. And we already also had this consideration that this implies that this leaf is compact. So that implies that this leaf is compact. Is a compact curve. Okay. Now, I must say that this case does not require parabolicity. You can even forget this notion, this condition. Okay? So this is a compact complex curve. And and now our current, this specific current, what is that? Which we have according to this proposition, which is listed here. We know that current T, so this current which was T was ddc exact. Okay, then it is closed, then there is a transverse measure, and we know how to reconstruct current from the transverse measure. So what is that? It acts on forms like that. So it integrates over the leaves in flow boxes form, and then it integrates against d mu over the transversalis, let's say d. Now, but our case is simple. This is a delta measure. So this is equal to the integral of the form over the p minus 1 of z, so over the piece of the leaf. Yeah? This is in the leaf. Okay? So that means that our current is a current of integration over this leaf. So we proved everything. So if we have a leaf with contracting holonomy of a foliation on exact manifold, then this leaf is compact, and the corresponding current is the integration over this leaf. So and this integration is the ddc exact current. Okay. Now, I'm going to stop more or less. Now, we want to prove this theorem also for the case when our foliation is tamed. There exists a taming form. And now, to prove this, we need to consider this object, the union of leaves which cuts some transversalis. Well, this is called a Poincar domain. Moreover, we need to consider the union of the universal covers. And this is the universal covering Poincar domain. And the problem, there is another problem here, that this guy might be non-Hausdorff. And the reason of being non-Hausdorff is very simple. These are vanishing cycles, which we already had in Novikov's theorem. So we should deal with vanishing cycles, and tamed foliations we break into two classes, for which if this thing exists as a complex manifold, is Hausdorff, then that means that the leaves of the foliation can be uniformly uniformized. You can construct universal covers uniformly. And such foliation usually one calls uniformizable. And then there is one more class. Well, there is a class which we had, which was exact. And there is one more class of foliations such that they contain vanishing cycles. And the aim of one of the aim of my course was to describe these foliations S, which admit, such that they had some leaves with vanishing cycles. And it turns out, so this will be a disjoint union, and it turns out that if you have a vanishing cycle, like in this definition which I gave, then you have a very strong object. Then you have, so vanishing cycle comes together with a strictly pseudo-convex hypersurface, which is a which looks like that, which you can see here. You take sphere, this is a strictly pseudo-convex hypersurface. It embeds into your manifold, and it carries also this vertical foliation. But this, now it's the only thing which can happen. Then you have something like, well, it will be not sphere, but it will be topologically sphere, but maybe ellipsoid or anything else, strictly pseudo-convex, and it has this vertical foliation locally around it, and then this thing can be embedded to your foliated pair, so leaves goes to leaves, in such a way that the image, well, this will be sigma, such that the image of the boundary will be not homologous to 0 in your manifold. So it's a very strong complex geometric object. And with this object you can work in the case when Poincaré domains are non-Hausdorff. I'm sorry I did not tell you anything about the proof in these cases. Okay, but I just give you the proof in some very some special one of 3 cases. Okay. Thank you.